Everyone that has ever ridden a bicycle knows it can be bliss to use the gears when going uphill. You might have to make more rotations with the pedals, but at least you can save your legs from exhaustion. How much strength you need to push down on the pedal, also known as rotational force or torque, and how fast the pedals need to turn, also known as speed, is determined by transmission. You can find transmission in all types of machines, for example, in an exoskeleton. Transmission controls the conversion of speed and torque from a rotating power source to something else that needs to move. In an exoskeleton, we need our joints to move at a certain speed and torque to safely move the legs of the pilot. We don't need the legs to move very fast, but we do want the joints to deliver enough force to carry the pilot. The transmission converts the fast rotations of the electric motor to slower movements of the joint, whilst increasing the torque, which is exactly what we need. There are different types of transmissions. Common drive elements that are used are a gear drive, which is used in, for example, old-fashioned watches, a belt drive, commonly used in mills, or a chain drive, which you might recognize from your bike. They all have their own advantages and disadvantages. For example, how well it can absorb vibrations, how well it can transfer heavy loads, and if it can handle fast speed reductions. In our exoskeleton, we use a special type of gear drive. If we know some key elements of the transmission, we can do some calculations. Let's assume we have a simple two-gear system and ignore machine efficiency. The transmission torque is determined by the ratio between the number of teeth on each gear. It can be calculated using this formula. The output torque is equal to the number of teeth on the non-powered gear divided by the number of teeth on the powered gear times the input torque. If the gear that is powered by the motor that has 15 teeth and the other gear has 30 teeth, the transmitted torque is twice as big. If you know how much torque you need, you can determine how much your motor should be able to deliver. Now that you know how to calculate the transmission torque, calculating its speed should be easy. It works exactly opposite of torque transmission. Just like how the torque increases with an increased amount of teeth, the speed actually decreases. It can be calculated using this formula. The output speed is equal to the number of teeth on the powered gear divided by the number of teeth on the non-powered gear times input speed. Can you see the only thing that has changed is the teeth ratio calculation? So let's say the powered gear moves at a rate of 10 rotations per minute. If we use the same gears again, the second gear will move at 15 divided by 30 times 10 equals 5 rotations per minute. So its torque has doubled, but its speed has halved. You should realize, though, that using these gears, the direction of rotation has changed from clockwise to counterclockwise. This is an example of a simple gear system. Like I said before, in exoskeletons, often a special type of gear drive is used, called a harmonic gearing. It looks quite complicated, but let's give it a go. In a harmonic gear, a flexible gear rotates within a rigid gear. If you take a look at this picture, you can see the outer blue gear, which is connected to the exoskeleton bone on one side of the joint. The red, flexible gear is connected to the bone on the other side of the joint. The green part, called the wave generator, rotates within a flex spline. This way, the red flex spline is deformed slightly and teeth are locked within the blue circular spine. For this to actually generate movement, the flex spline has a few teeth less than the circular one. In this animation, it has 2 teeth less. For every full turn of the green wave generator, the flex spline rotates only 2 teeth. If you look closely and focus on one single red tooth, you can see it move 1 slot further with every half rotation. You can perform similar speed calculations on this harmonic gear as we did on the simple 2-gear example. The formula looks slightly different though. The speed can now be calculated by subtracting the number of flex spline teeth from the number of circular spline teeth, divided by the number of flex spline teeth, and times the speed of the wave generator. Keep in mind that similar to the simple gears, the direction of rotation changes. As you can see, different types of transmissions have slightly different formulas to calculate transmission speed and torque. If you know how to use them, you can choose the right motor and transmission for your exoskeleton. Let's try and do some calculations on transmission in the next exercise. Good luck!